In the previous lecture, we have introduced about compaction and different methods for compacting soil, and we also discussed a method of compaction in the laboratory called standard Proctor test after R. Proctor 1930, and we also discussed the distinguished behavior between compaction of soils for cohesionless soils and cohesive soils. So, in this lecture, we will try to understand much about principles of compaction and the role of water played in the compaction process, and we will also discuss the factors affecting the compaction characteristics of soils, and along with another modified Proctor compaction test which has been developed for highway and subgrade works by ASTO. So, in the previous lecture, we have seen about a definition of compaction and compaction of cohesionless soils and cohesive soils. We also seen a small demonstration how different cohesionless soils and cohesive soils are, and laboratory compaction method we have seen standard Proctor compaction. So, in this lecture we will be discussing about modified Proctor compaction test, and principles of compaction and water density relationship has been introduced to you. So, here we will be discussing about the role played by water in the entire compaction process along with the factors affecting the compaction. So, this lecture is compaction of soils part 2. So, as we have defined, let us look once again. Compaction is a process that brings about an increase in soil density or unit weight. So, here in the compaction, the degree of compaction is also measured as dry density or dry unit weight. So, compaction is a process that brings about an increase in soil density or unit weight accompanied by decrease in air volume. For example, if you see here for the loose aggregate, if the work is applied to this, then these aggregates are rearranged into the closer positions. In the process, what we are doing is that we are shunting the air in the presence of a wear which is there in between the void spaces between the solid grains. So, this we will say that the soil is said to be in a compacted state. So, compaction is a process that brings about an increase in soil density or unit weight accompanied by a decrease in volume. So, by removing the air, so the aggregate particles will be tucked into the closer positions to increase the density of solid grains in a given volume. So, in the previous class we have discussed that the relationship between dry unit weight and water content can be obtained by standard Proctor compaction, and we said that it is of typical a bell shaped nature curve. So, here in this figure once again the same curve is shown for you, where you see and water is helping the compaction up till this process. So, as you climb onto the limb here, you will see that the density, dry density is increasing with an increase in water content, and after reaching certain point you are observing that the dry density keeps falling with an increase in water content, and this line we said that 0 air voids line or 100% saturation line. We will be discussing more about this in this lecture. So, we said that and we defined this point at which maximum density exists is called the maximum dry density of a given soil, and the corresponding water content is termed as the optimum water content or optimum moisture content. It is indicated as OMC, optimum moisture content for a given soil. So, these values are unique for a given soil depending upon the soil type, and it is a comparative effort whatever you are given, or the gradation or a combination of the different factors will be able to influence this particular values gamma D max, that is maximum dry unit weight, and optimum moisture content. Let us look into this mechanism once again. So, as we have seen, when the moisture content or water content is less than optimum moisture content. So, if that is the case, we will generally refer that as dry of optimum. If the moisture content is less than the optimum moisture content, then we refer that as dry of optimum moisture content or dry of optimum, which has got a practical relevance in compacting soils. So, when a moisture content is less than OMC, soil is stiff. Naturally, the water is less. So, soil is stiff and difficult to compress, because the friction between the grains is very high and is very difficult to shunt more air from the soil mass. So, low density and high air voids can be obtained, because more air cannot be shunted out, because the friction which is there between these stiff particles will not allow us to shunt the air from the soil mass. So, when the moisture content is less than OMC, soil is stiff and difficult to compress, and because of that the low density or low dry unit weight prevails and high air voids can be obtained. Now, increase in moisture content lubricates. That means that as you keep on increasing water content from say 5%, 6%, 7% like that. So, this addition of water to a given soil mass softens the soil. So, in the process it softens the clay bonds or bonds between the particles and reduces the surface tension forces, because previously these forces are inhibiting the particles for coming close within the soil mass and makes it more workable. So, in the process what will happen is that the particles will take a closest position as possible for a given soil. So, because of this higher densities are achieved and low air voids can be obtained. So, it is not that 100% air voids will be removed, but low air voids will be achieved. So, increase in moisture content lubricates and softens the soil. So, here we should appreciate the role played by the water in compacting the soil. So, here water plays as a lubricating agency and softens the clay bonds. So, in the process what will happen is that reduces the surface tension forces within the soil and makes it more workable, and higher densities and low air voids can be obtained. So, this is very important concept we should remember about the principles of moisture density and compaction. Increase in moisture content lubricates and softens soil, that is, in the process softening of clay bonds occurs and reduces the surface tension forces within the soil and makes it more workable. Because of this higher densities and low air voids obtained. Now, as the air content becomes less, you see here in this slide it has been described here, the water and air in combination tend to keep the particles apart. So, now once we cross this optimum moisture content, as air content starts becoming less, it is not that it is reducing to 0, air content becomes less and the water and the air combination tend to keep the particles apart and prevent any appreciable decrease in the air content. So, the appreciable decrease in the air content means it will never go into a completely saturated state, it will always remain in the partially saturated state. The total air voids however continue to increase with moisture content, hence the dry density of the soil falls. So, what will happen is that in the process what will happen is that if you see when the water starts occupying the space between the grains. So, air and water which is actually inhibiting the particles from coming close once we cross this optimum moisture content. So, the optimum moisture content is a threshold limit for that particular soil. So, once we cross that, what will happen is that the particles will not come closer because of the presence of air and to some extent excess amount of water, which actually inhibits the particles from coming close. So, because of this, another thing is also that the unit weight of water or the density of water is much less compared to density of the soil solids. Because of that, on your you will see on the right hand side of the optimum moisture content, with an increase in water content the dry density falls. On the left hand side of the optimum moisture content, that is the dry of optimum, you will see with an increase in water content there is an increase in the dry unit weight, but there is a peak at which the maximum dry density which occurs at a particular water content. So, that we referred as a maximum dry unit weight and optimum moisture content for a given soil. To the right of OMC, the curve approaches saturation line, but never reaches it is never possible to expel the entropy. That is what actually has been discussed. So, for compaction of soil, whenever we draw a 0 air voids line, the compaction curve is always on the left hand side of the 0 air voids line. It never crosses or it never touches that. If it touches, it means that a 100% saturation is achieved. That is conceptually wrong in the process of compaction. So, to the right of OMC, the curve approaches saturation line, but never reaches. So, it is never possible to expel all the entrapped air. This is also explained in the forthcoming slides. So, let us consider in this slide uncompacted soil and compacted soil. So, here you see a three-phase diagram is again drawn with an uncompacted soil, solids, water and air with it. So, you will see that more amount of air and water and solids. This may be from the borrow area which has come from the certain area for compaction. So, this is, let us assume that we applied a certain energy, a compactive effort to compact the soil, and we were able to successfully remove a certain amount of air. So, this is a modified three-phase diagram where for a compacted soil which is shown here, air, water, solids. If you see a theoretically maximum degree of compaction is that this, once you are able to shunt all the air out of the voids. So, in practice this dry unit weight is never achieved, but it represents the theoretical upper bound for a theoretical maximum degree of compaction. So, if you see here, this is the case actually is possible only theoretically only. So, theoretically we can say that this is the maximum degree of compaction, but in practice this dry unit weight is never achieved, but it represents theoretical upper bound. That means that this air which is there in the compacted soil cannot be shunted out, whatever may be the energy which is applied to the soil. So, that is what actually this slide shows, an uncompacted soil with air, water and solids with a three-phase diagram, and a compacted soil with a decrease in the air content, and which shows that there is a compacted nature of the soil exists. And this diagram shows a two-phase diagram again with water and solids, which is a theoretically possible degree of compaction, and we also said that in practice this dry unit weight is never achieved, but it represents the theoretical upper bound. So, to better understand the compaction, consider again the three-phase diagram for soil shown below. So, let us consider that a three-phase diagram once again. This we have discussed in the previous lectures, air, water, solids, and on the left hand side you will see volume, that is volume of air, volume of water, which is total put together is volume of voids and volume of solids. And here on the right hand side, weight of air is equal to 0 and weight of water is equal to water content times weight of solids, and Ws is the weight of solids. So, water content is the ratio of weight of water to weight of solids. So, the total weight of a soil mass here is Ww plus Ws, and total volume of the soil mass is Va plus Vw plus Vs. So, we knew that from the definition of void ratio, void ratio E is equal to ratio of volume of voids to volume of solids, and degree of saturation is ratio of volume of water to volume of voids. So, these are the important things which we have to remember, and we can reduce gamma bulk, or we can write gamma bulk from this diagram as Ww plus Ws divided by total volume. So, by rearranging and writing for W is equal to Ww by Ws, then we can write gamma bulk as W plus 1 into Ws by V. So, Ws by V nothing but gamma D, that is the dry unit weight. So, if you know the bulk unit weight of soil mass, we can calculate gamma D dry unit weight by this relation, gamma D is equal to gamma bulk by 1 plus W. So, in the compaction test, when we add a known amount of water content to this, and what we get by weighing the mold is the bulk unit weight, that is weight of soil mass including solids, water, and divided by the total volume, which includes volume of air, volume of solids and volume of water. With that, we will be able to estimate the bulk unit weight. The bulk unit weight divided by the water content plus 1 will give us the dry unit weight. So, that is actually is an expression which is widely used in the compaction of soils. So, recall that we are just going into the analysis of this compaction curve. So, recall that we knew gamma D is equal to Gs gamma W by 1 plus E. We have derived for this for dry soil, that is two-phase soil, gamma D is equal to Gs gamma W by 1 plus V. So, for a given water content W, the maximum degree of compaction that can be achieved is when all of the air voids have been removed. That is what we have said, and let that will be achieved once the degree of saturation SR is equal to 1. So, since SR is equal to WGS by E, so we knew that E is equal to WGS by SR for a partially saturated soil. The corresponding void ratio for SR is equal to 1 can be obtained as E is equal to WGS. So, for substituting for E is equal to WGS, we can obtain gamma D is equal to GS gamma W by 1 plus WGS. So, gamma D, that is along the 0 air voids line or 100% saturation line, can be obtained by GS gamma W divided by 1 plus WGS. So, this by using this expression we will be able to determine for a, by knowing specific gravity of the soil, by knowing water content at which this is the range of water contents for a given soil, we will be able to estimate the dry unit weight along the 0 air voids line. So, along this line the degree of saturation is 1, the SR is equal to 1 is valid along this particular for this expression. So, this represents the highest degree of dry unit weight that is possibly achieved for a given water content W. So, this particular unit weight, dry unit weight gamma ZAV is possibly achieved for a given water content W. So, for a given water content W, the maximum degree of compaction that can be achieved is when all of the air voids have been removed. So, we have substituted for E is equal to WGS by SR, and SR is equal to 1, and we substituted E is equal to WGS, and we obtained this expression for gamma D ZAV is equal to GS gamma W by 1 plus WGS. Now, let us see whatever we have discussed in the form of a curve. On the left hand side here, the dry density is also mg per meter cube, or the dry unit weight in kilonewton per meter cube can be represented on the y axis, and water content or moisture content is represented on the x axis. You see, this is a compaction curve, a bell shaped compaction curve which is shown here, and this is a saturation line. So, this is what we are referring as a 100% saturation line or 0 air voids line. So, this particular line is also referred as 0 air voids line or 100% saturation line. So, air void lines for a given particle density can be obtained for 5%, 10%. That means that these are all 5% air voids, 10% air voids, or 100% saturation line, 95% degree of saturation line, or 90% saturation line. So, that is how these lines are plotted. In order to plot these things, we, as we discussed in the previous slide, we have to use this expression like gamma D is equal to GS by 1 plus W by SR into GS into gamma W. So, for SR is equal to 1, that is 100% saturation line, we will get this line. Say for degree of saturation is say 0.95, then substituting this by for the range of water contents, we will be able to find out this particular line. These particularly in terms of air void lines are determined by using this expression. For example, gamma D is equal to GS into 1 minus NA divided by 1 plus WGS into gamma W. By using this expression for a range of water contents, we will be able to determine dry unit weight of a given soil moist. So, for example, NA, which is nothing but volume of air in total volume of the soil mass. So, that is the percentage air voids we have defined earlier. So, by using that NA is equal to VA by V, we can determine this 5% air voids line or 10% air voids line, or in terms of a degree of saturation line, we can determine like 80% degree of saturation. For 80% degree of saturation, SR is equal to 0.8. For a range of water content, we can even determine 80% saturation line. Another thing which is required to be discussed here is that we knew that percentage air voids is equal to N into 1 minus SR. So, percentage air voids is equal to porosity times 1 minus SR, which is nothing but percentage air voids is equal to N times AC, which is nothing but the air content. Air content is defined as volume of air in total volume of voids. So, air content definition is different from the percentage air voids. So, with this definition, a 20% air content line is not equivalent to 80% degree of saturation line. So, that difference is required to be noted. Many notations are there for plotting air content lines in the form of these air voids lines can be plotted in terms of a degree of saturation lines or air voids lines or air content lines. One thing which is required to be noted is that 20% air content line is not equivalent to 80% of degree of saturation line. That is because of this particular definition which is lying between AC is equal to volume of air to total volume of voids, or NA is equal to VA by V. Now, let us discuss about this particular saturation line, 100% saturation line or 0 air voids line. So, saturation line is a hypothetical line. We said that in the field it is not possible to achieve this density, but this is an hypothetical line which exists on the right side of the compaction curve, and points on the line denote the density for completely saturated conditions at respective water contents. So, with this is not possible to achieve this particular density because the air cannot be shunted out of the voids. So, points on the line denote the density for completely saturated condition at respective water contents. It is the maximum possible dry density for any soil. This is the maximum possible dry density for any given soil, and practically it is not possible to achieve this density. That is what we have discussed earlier also. And dry density for saturation line is given by, again I am giving this expression here, gamma D is equal to gamma W into 1 by Gs plus W. This has been deduced earlier. So, for a range of water contents we will be able to determine the gamma D or the dry unit weight or dry density. So, saturation line is a hypothetical line, and points on the line denote the density for completely saturated condition and respective water contents. So, having seen about the principles of moisture content and principles of compaction, now let us look into the another method of determining compaction characteristics of a soil by using a method called modified compaction test or modified Proctor compaction test or ASTO compaction test. So, this is also called as it is written here, ASTO or modified Proctor compaction test. The standard Proctor's test is not sufficient for highways and highways. Basically, during the construction of airways and highways, it was felt that the compaction whatever is being given in the form of a standard Proctor compaction is not adequate for the soils. Should be possible to compact the soils by increasing the compactive effort. So, that was actually made possible by using this particular method, modified Proctor compaction test. This was adopted by US Army Corps of Engineers. US Army Corps of Engineers developed this method and modified compacted test, and which used greater levels of compaction than whatever we are saying in the standard Proctor compaction test, and produced higher densities. So, by supplying higher densities to the soil, that means that in order to overcome these frictional forces which are in between this solid grains, you need applying certain amount of more energy will be able to push the particles closer by shunting the more air. So, with the process we will be able to achieve more dry unit weight, and may be possible that at less water contents the optimum moisture content can be achieved of this because of this phenomena. So, modified Proctor test was later adopted by ASTO and ASTM. So, ASTO and ASTM even today adopts this modified compaction test, and basically used for compacting soil for highway subgrades and air strips. Basically, to construct air strips on soils, they require very solid subgrades for resisting the impact of landing of the aircraft and all. So, for that this particularly the modified compaction test is used for compacting the subgrade while preparing for these air strips. So, let us look into the details about modified Proctor compaction test. It is similar to Proctor compaction test. It is done in the same mold, but it is more energy is applied to the soil mass, so that the air which is there in the voids can be shunted out to produce more dry density and at less water content. So, internal diameter of the mold is 105 mm, the same mold which is used for standard Proctor compaction test. Height of the mold is 116 mm. Mold has detachable collar and base plate assembly, and mechanically operated rammer has a face diameter of 50.8 mm, that is 5.8 8 centimeter, 5.08 centimeter, and a free falling weight of 4.5 kg, and the height of drop is 0.45 meter. In the case of standard Proctor compaction test, we have used 2.5 kg hammer falling at a height of 30 centimeter or 0.3 meters. In this modified Proctor compaction test, we are using a standard a Proctor hammer of face of diameter 50.8 mm with a hammer weight of 4.5 kg, falling weight of 0.45 meters. So, if you compare here, the number of blows are 25 per layer. In the case of standard Proctor compaction test also, we have used 25 blows per layer. Number of layers are 5 layers. In the standard Proctor compaction test, we have used 3 layers. So, we can see the degree of compaction energy what we are applying. The weight of hammer is 4.5 kg in modified Proctor compaction test. In case of standard Proctor compaction test, it is around 2.5 kg. And falling height is 0.45 meter in modified Proctor compaction test. In case of standard Proctor compaction test, it was 0.3 meter. So, when you, similar to whatever we have done for standard Proctor compaction test, if you compare, if you compute the compactive effort, the compactive effort is given by 4.5 into 0.45 into 5 is nothing but the number of layers, into 25 blows per layer divided by the volume, and then normalization of the units, will get the energy equivalent to 25,3125 kg meter per meter cube. So, this energy whatever the compactive effort is 4.5 times the compactive effort in the standard compaction test. So, by giving this 4.5 times the extra energy with this modified Proctor compaction test, it is possible to compact the soils as close as possible to the maximum possible position and expel the air quickly, so that maximum dry density can be achieved at the possible low water contents. So, the procedure is similar to standard Proctor compaction test. The differences have been discussed already. So, approximately 5 kg of soil is thoroughly mixed with 4 to 6% water content as a depending upon the judgment, this has to be decided, and weigh the mold without base plate and collar, fix the collar and base plate, and in the mold compact the weighed soil in 5 layers, giving 25 blows per layer with the 4.5 kg hammer. So, same principles whatever we have discussed for the standard Proctor compaction then holds good here also, and weigh only mold and soil after making soil flush with the mold edges. So, that weight has to be taken. Then remove the sample from the mold and slide it vertically to obtain a small sample of moisture content determination. So, though we knew the amount of water we added, it is customary to determine the water content for each trail. So, thoroughly break up the remainder of the material and increase the moisture content by 1 or 2% and repeat the above procedure for each increment. So, continue this series of determination until there is either decrease or no change in the wet unit weight of the compacted soil mass. Generally, there will be a decrease in the wet unit weight of soil mass occurs, because the process is that the water starts entering in between the solid grains. As the unit weight of the water is much less compared to the unit weight of the solids, because of that the dry density is falling on the right side of the optimum moisture content. So, in this particular slide, what we have shown is that dry density versus moisture content, and we have compared ASTO or modified Proctor compaction test or standard Proctor compaction test or light compaction test. In the case of Indian conditions, it is also called IS light compaction test, IS Indian standard light compaction test. So, in British standards, this particular slide for the British, so it says that British standard heavy compaction test or British standard light compaction test. So, here this is a compaction curve obtained for IS light compaction, where you can see a 2.5 kg hammer has been used with a fall of around 0.3 meter, and this particular curve is a compaction curve with maximum dry unit weight is around 1.95 mg per meter cube or so, and with a water content of around 15% optimum moisture content, and this particular curve is around 19% or 18% optimum moisture content with 1.81, where you will see here the increase in dry density indicates that more amount of air could be expelled quickly, so that the additional amount of dry density has come to this particular so that this is actually the effect of compaction energy on the soil, which we will be discussing in detail in the forthcoming slides. This line shows the saturation line, which has been obtained from this particular expression gamma D is equal to gamma W into 1 by Gs plus W. So the energy difference between these two is around 4.5 times. So here this curve is obtained by giving an energy of 4.5 times the energy of this particular curve. So you can see for a Proctor compaction test, that is modified Proctor compaction test, you will see that the curve shifts to the left hand side and shifts vertically upwards. That indicates that the soil particles are coming closer by expelling the air quickly. So this additional energy is actually enabling the air to be expelled quickly from the soil solids. So that actually makes this particular difference between these two. So this is optimum moisture content. What has been shown here is 13.5% and 18%. You can see the optimum moisture content could be shifted by around 5.5% to the left hand side, and the density here previously it was around 1.82, now it is 1.95. So an increase in the density could be attributed to this particular compaction energy which has been given. So the importance of the Proctor test, if you look into it, it gives the density that must be achieved in the field. Otherwise, for a given soil, once you have a soil before compacting in the soil, we should know the compaction characteristics of the soil. So then we know that to what degree of compaction we can compact the soil. So it gives the density that must be achieved in the field. So that is actually is possible with either, depending upon the test, either due to standard compaction or due to modified Proctor compaction, you can determine the density that must be achieved in the field, and provides the moisture range that allows for the minimum compact effort to achieve the density. So it also tells us that what range the soil should be maintained, so that the density can be, maximum density can be achieved. So otherwise, for a given soil we will not be having this information, then we will face in difficulties in compacting the soil. Provides the moisture range that allows for the minimum compactive effort to achieve the density, and provides data on the behavior of the material in relation to various moisture contents. So it also gives us how the material behaves by varying the water contents. So the behavior can be different for different soils. So it gives a data, provides a data on the behavior of the material in relation to various moisture contents, and it is not possible to determine whether a density test passes or fails without it. So it is not possible to determine whether the density test passes or fails without it. So the Proctor test has got a maximum relevance, and is also used widely even today in the construction of embankments, construction of roadways, construction of airways widely, to determine the first job is to assess the compaction characteristics of soil in the laboratory, depending upon the type of application, either with the use of standard compaction test or modified compaction test, and obtaining those properties for a given soil. Suppose if you have got in a soil 2 or 3 different borrow materials, so all these 2 and 3 borrow materials have to be ascertained to understand their or to obtain gamma D max and OMC, that is maximum dry unit weight and OMC. See, each soil will have a unique variation, because they entirely depends upon type of soil and gradation and the composition of the soil particles and mineral which is present in the soil. So all these things will add to the behavior of this particular compaction. So having seen the methods for determining compaction characteristics of the soil in the laboratory, very soon we will be discussing about the field compaction methods and how we compare compaction. Basically we compare by using a term called relative compaction, that we will be discussing later. So this relative compaction or relative density, which is different for cohesionless soils and cohesive soils. So we will be discussing the field compaction methods separately for cohesionless soils and cohesive soils. Before that, let us look different factors affecting compaction. So, factors influencing compaction are moisture content, soil type and effect of compactive effort. So, if you look into it, the moisture content and soil type and effect of compactive effort are the major factors which influence the compaction process. And in the effect of compactive effort, the nature of the effort and load duration and area of contact. So, this also the area of the contact, particularly for cohesive soils and all, which is very much important, and the amount of effort which has been applied also comes into the picture. So, let us list the factors influencing the compaction. If you list, then moisture content comes into in the first place, then soil type and an effective compactive effort. So, an effective compactive effort is again subdivided into nature of the effort and amount of effort. Nature of effort is again subdivided into the duration of the load which is applied and area of the contact. So, let us discuss each factor one by one. As you seen the moisture content, we also seen that the importance of the role played with the water in the compaction. So, let us look how the soil behaves on the dry of optimum and wet of optimum in this section. At low moisture content, it has been documented here. At low moisture contents, the strength of the clay lumps and friction between granular particles is high. So, given compactive effort will not be able to remove all air voids leaving the soil in overall compressible state. So, the soil is almost in a compressible state because the more grains are present, more air voids are present in the. So, in the process what will happen is that if you look into this in this case, you will see that between the solid grains the more amount of air is still present, which could not be removed because of the difference which is discussed here. So, this is the air which is remained in the voids, causing the soil in a putting the soil in a overall compressible state. When it is subjected to stresses, what will happen is that further these layers are layers of a fill or a structure, and is actually they will be in a potentially collapsible state, because with the stresses and all, these particles will try to come closer, and in the process the entire structure, for example, if this is there in say an embankment of certain height, so because of this particular embankment can be subjected to some settlements. So, with this process what will happen is that it may lose the serviceability state and all. So, this particular thing should be avoided, like at low moisture content the strength of the clay lumps. Suppose if this is taken as a clay lump and friction between the granular particles will not be able to basically it hinders to remove the air which is there in the voids. So, entire soil mass remains in a collapsible state with the application of the stresses. So, this is actually which is required to be noted. So, at low moisture contents, the strength of the clay lumps and friction between the granular particles is high. So, a given compactive effort will not be able to remove all air voids, leaving the soil in an overall compressible state when it is subjected to stresses from further layers of fill or a structure, and is actually potentially in a collapsible state. Secondly, so we have seen with low moisture content. Now, let us look at high moisture contents, what will happen. That is, at high moisture contents, clay lumps become weaker because they try to become softened, and with that in the process they try to become the bonds between the clay lumps try to weaken. So, in the process the friction between the granular particles will be reduced. So, in this process the air voids are more effectively removed, so that the dense matrix can be achieved. So, more easily removed during compaction. So, the moisture content at which the maximum dry unit is attained is generally referred as the optimum moisture. So, this one if you see, as we go on increasing the water content, there is a particular state will come at which water content at which this maximum dry unit weight is possible, that is we have termed as the maximum dry unit weight. So, at high moisture content, clay lumps become weaker and the friction between granular particles reduced, so the air voids are more easily removed during compaction. The moisture content at which the maximum dry humidity is attained is generally referred to as the optimum moisture content. This we have defined earlier and we are actually defined once again with respect to a factor as a moisture content. Now, another thing is that at moisture content above the optimum moisture content. So, we have reached up to optimum moisture content. Now, we go towards the right hand side of the optimum moisture content, that is wet of optimum. At moisture contents above the optimum moisture content, the soil particles cannot move any closer together, because even the most of the air has been expelled and there is more water present in the voids. So, in this diagram, particularly the volumes, that is volume of solids, volume of water and volume of air is shown on the y axis and moisture content is shown on the x axis. If you see here, this is a combination actually which has been achieved. There is a certain optimum water content at which the maximum dry unit weight is possible, that is actually this one. So, you can see that there is a certain amount of air, less amount of air than initially on the dry side of the optimum, much dry side of the further of the optimum, dry side of the optimum, you will see that more amount of air is there, but that we could come across, we could overcome by supplying more water to the grains. We could able to shunt the air and gradually you can see the depleting stage of the air, but it never goes to 0 here. So, you will see that the depleting air which is there. So, this is the volume of the air portion and this is the volume of the water portion. So, once we cross this particular optimum moisture content, you see that amount of water is available between the voids is keeping on increasing. So, in the process what will happen is that, as we have discussed, that raw water is much less than raw solids. Because of this process, you will see that they also throws an explanation for why the dry density decreases with increasing moisture content on the wet side of optimum. So, having seen the moisture content, let us look another factor which is called soil type. So, soil type basically grain size, because particle size distribution, which is we have discussed earlier how important it is, and shape of the soil grains, whether angular or round sub-rounded aggregates or plate shaped particles. So, the different particles can be there in a given soil mass. So, amount and type of clay minerals. So, we also discussed the different type of clay minerals, for example, kaolinite, illite and montmorillonite, and different characteristics of the minerals have been discussed. So, and the specific gravity of the soil solids, for example, if it is of iron origin, then the specific gravity of the soil solids may be very high. Sometimes if it is of say a fly ash can have a low specific gravity. So, the specific gravity of the soils also, soil solids also influence the dry unit weight and have a great influence on the gamma D, the dry unit weight and optimum moisture content. In poorly graded sands, the dry unit weight initially decreases as the moisture content increases and then increases to a maximum value with further increase in moisture content. Basically, in a poorly graded sands, particularly sands have got a different phenomena, that is cohesional soils have got a different phenomena, which is actually explained as in the form of a bulking phenomena of a soils which is possible. So, in moist conditions the volume appears to be very high, and because of that what will happen is that there will be some capillary forces which will be there between the grains, and then these grains will induce some apparent cohesion between the particles and will hinder the particles from coming closer. So, in the process what will happen is that the density decreases, and after adding certain amount of water, these films which are surrounded by the particles will get washed out, and possible that particles will change to the closer positions. So, in poorly graded sands, the dry unit weight initially decreases as the moisture content increases and then increases to a maximum value with further increase in moisture content. At lower moisture content, the capillary tension inhibits the tendency of soil particles to move around and be compacted. So, at lower moisture content, the capillary tension inhibits the tendency of soil particles to move around and be compacted. So, we have discussed about different factors affecting the soil, and we also seen that different soils are possible. So, in the process, in this particular slide, a compaction curves for different soils are shown, that is compaction curve effect of soil type, and this is the 0 air voids or 100% saturation line. So, this is for a uniformly graded sand. That is the reason why when we are discussing about desert sands which are poorly graded in nature or uniformly graded in nature, which will be difficult to compact them. So, you can see a difference between a uniformly graded sand and a well graded sand. The well graded sand is the one which is maybe an ideal with something like a fuller characteristic curve. With that, we will be able to get the maximum dry unit weight and less closest optimum moisture content. So, a distinguish should difference in behavior between a well graded sand and uniform graded sand can be seen. Then another difference which is required to be noted is a clay of low plasticity, a lean clay and a fat clay. A fat clay is the one which is more plastic in nature, a lean clay is the one which is low plastic in nature. With that, a difference in behavior can be seen here, and a sandy clay has supposed to have certain higher density compared to clay of low plasticity, and this is a particular curve which shows for gravel sand clay mixture. So, gravel sand clay mixture something like a combination where gravel particles are there and sand particles are there and the clay particles are. So, different types of particles are present in this. So, in the process we will be able to get the maximum possible dry unit weight and at a certain water content here. So, compactability or ease with which soils can be compacted will depend upon the soil type. So, you see that a different soils have got a different types of compaction curves. A uniform sand has got a different curve, and a difference in a silty clay, for example, a lean clay or a clay with high plasticity. So, there is a certain difference we will be discussing, and a difference in distinguishable behavior between a well graded sand and the uniform sand also can be seen. So, compactability or ease with which the soils can be compacted will depend upon the soil type. So, this is an important thing which we should remember whenever we are dealing with the compaction characteristics of soils. So, we have seen in the previous slide at a given moisture content, a clay with low moisture content, that is a low plasticity will be weaker than a heavy or high plastic clay. So, it will be easier to compact. So, at a given moisture content, a clay with low plasticity will be weaker than a heavy or highly plastic clay. So, it will be easier to compact. So, the reason is attributed to. So, let us look at the why reason. We have seen that two distinguishable behavior for silty clay, that is lean clay and fat clay. We knew that the liquid limit of a fat clay will be higher than the liquid limit of a lean clay. So, for a given compact effort, the air voids can be removed more easily for a low plasticity clay, and because it will have a low moisture content anyway and a higher dry unit weight can be obtained. So, because the silty clay is weaker in strength, the clay lumps are soft in the nature. In the process, with a given compact effort, you will be able to shunt air more quickly, and because of that the closer position is possible for the given matrix. With that, we are able to establish for a given compact effort, the air voids can be removed more easily for a low plasticity clay, and because it will have a low moisture content anyway. So, a higher dry unit weight can be obtained. Let us look into another factor which is called effect of compactive effort. This can also be discussed something like a amount of compactive effort which is applied. It is not that when you apply more and more blows of a to the soil, it is the soil particles will be able to be compacted to the maximum possible densities. There is also a certain optimum compactivity is required to be applied to the soils. By applying more, there is no use, we will be creating an instability in the soil matrix. So, maximum dry unit weight increases with increase in compactive effect. So, maximum dry unit weight increases with increase in compactivity. That is possible by increasing the compactive effort. We will be able to see the maximum dry unit weight increase, and increase in compactive effort decreases the optimum moisture content to some extent. That is why we have seen whenever we applied modified in the more energy in the case of modified Proctor compaction test, we have seen that the curve shifted to the left hand side and compared to left hand side and upwards compared to a standard Proctor compaction test. So, increase in compactive effort decreases optimum moisture content to some extent. So, if you look this effective compaction, effect of compactive effort. So, applying more energy to the soil will reduce the air voids content further and increase the dry unit weight. applying more energy for a soil will reduce the airwads content further and increase the dry unit weight. For example, if you see on the curve here, a dry unit weight is shown and moisture content is shown on the x axis. You will see this particular curve is obtained with 20 blows per layer, and this for 25 blows per layer, and this one for 30 blows per layer, and this one is for 50 blows per layer. So, as you increase the compaction energy in this direction, you will see that there is an increase in the dry unit weight and decrease in the optimum moisture content. So, the line joining these optimum moisture contents is called line of optimums or optimum line. So, this is the line which is almost parallel to the zero airwads line, is the optimum line, which is nothing but this line joins the line of optimum moisture contents and maximum dry unit weight for a given compactive effort. So, with increase in compact energy, you see that the curve is shifting towards the left hand side. So, more compaction energy can beneficial especially for soils dry of optimum. You will see that more compaction energy can beneficial especially for the soils on dry of optimum. If you compact the soil on the wet of optimum, there is a possibility that the development of excess pore water pressures can take place, and which these pore water pressures they locked inside and create a case of some instability to the soil and result in a failures of structures which are constructed with this process. So, applying more compaction energy can be beneficial especially for soils dry of optimums. That is the reason, suppose in a particular compaction process, if compaction is done, if the soil is found to be wet in the site, it is allowed to dry. It is advisable to allow for drying, and so that the soil attains a particular state where it is possible for us to compaction. So, more compaction can be beneficial especially for soils dry of OMC. So, if a soil is already moist, weaker and above OMC, then applying more energy is wasteful, since air can quickly be removed. Applying large amounts of energy to a very moist soil may be damaging, since no more air can be expelled, but high pore water pressures can build up, which could cause slope instability during construction. That is what we have discussed. Slope instability could be caused during construction, or consolidation settlements as they dissipate after construction. So, these excess pore water pressures or pore water pressures which are developed by applying the energy to the wet soil already, these pore water pressures are locked in the soil, which actually causes the instability to the structure. So, in this lecture, we have tried to understand about again role played by the water in the compaction process, and the method of compaction by applying more energy, that is called modified Proctor compaction, and we try to compare laboratory compaction under standard compaction conditions and Proctor compaction conditions, and we also discussed factors affecting the compaction process, mainly moisture content, soil type and compactive effort.